Since the rocket age first took off during World War II, choosing the right fuel has always been a hot topic among scientists. Back then, rockets ran on things like ethyl alcohol, kerosene, or, in more advanced cases, liquid hydrogen. Sure, they worked, but they came with major downsides: pollution, inefficiency, and worst of all, they weren't suitable for the long journey. That's why SpaceX is believed to be leading the charge with a whole new kind of rocket fuel. The propellant used in Starship isn't just different from what we've seen in the past, it's a game changer in terms of performance, efficiency, and cost. More notably, SpaceX itself even has an ASU fuel production project that has already been approved. So what exactly makes this new fuel so special, and why is it considered a key ingredient for reaching Mars someday? Let's dive into today's episode of Alpha Tech. During World War II, under the direction of German scientist Wernher von Braun, Nazi Germany developed the A4, the first true rocket in history. It made its first successful flight on October 3, 1942, and became the world's first liquid-fueled ballistic missile. The A4 ran on a mix of ethyl alcohol, essentially diluted alcohol, and liquid oxygen, a type of oxidizer that's still used today in many modern rockets, including SpaceX's Starship. With a range of about 320 kilometers and a peak altitude of 80 to 100 kilometers, the A4 was the first human-made object to cross the Kármán line, the official boundary of space. There were several practical, technical, and economic reasons why Dr. Wernher von Braun and his team chose ethyl alcohol as the main fuel for the A4 rocket during World War II. First, ethyl alcohol was relatively easy to produce and widely available in Germany at the time. It could be distilled from potatoes or other plant sources, helping reduce dependence on scarce wartime resources. When combined with liquid oxygen as the oxidizer, it created a stable combustion reaction, providing enough thrust to power the A4 to a range of several hundred kilometers, with a specific impulse of around 250 seconds. Second, although there were alternative fuels at the time, like kerosene, it hadn't yet been refined into the high-grade RP1 we use today. And while liquid hydrogen had been discovered and experimented with as early as 1898 by British physicist James Dewar, large-scale production and safe storage were far too complex for the 1940s. In contrast, ethyl alcohol was far easier to handle and store under the technological conditions of wartime Germany, especially when rockets had to be mass-produced under extreme pressure. Despite its early advantages, ethyl alcohol was soon replaced after the war by a more advanced fuel, RP1, a highly refined form of kerosene. RP1 offered a higher specific impulse, around 280 to 310 seconds, compared to just about 250 for ethanol, which meant better performance and greater payload capacity. It also had a higher energy density, allowing for more compact fuel tanks and lighter rocket designs. Another key benefit was storage. RP1 has a high boiling point, around 217 degrees Celsius, so it didn't require the deep cryogenic cooling needed for liquid hydrogen or methane, making handling easier and cheaper. By the 1950s, the US and Soviet Union had steady oil supplies, allowing them to refine RP1 at scale. Its clean combustion and low impurities made it ideal for rockets like Atlas, Redstone, and the Soviet R-7. As space missions grew more demanding, from launching satellites to reaching the moon, RP1 became the industry standard for first-stage propulsion. Even today, RP1 powers SpaceX's Falcon 9, with over 500 successful launches. But for the next generation of rockets, especially one designed to be fully reusable and go to Mars, RP1 just isn't enough. So, why did SpaceX choose liquid methane for its Raptor engines? What makes it better than hydrogen or RP1? The answer is surprisingly simple: efficiency. For any rocket, the dry mass, meaning the total weight of the vehicle without fuel, typically makes up only a small fraction of its fully fueled weight, usually somewhere between 5% and 25%. Take the Space Shuttle, for example. If we count just the orbiter and the two solid rocket boosters, and not the massive external fuel tank, its dry mass was about 165,000 kilograms. When fully fueled, the entire system weighed around 2 million kilograms, putting its dry mass ratio at roughly 8.3%. Starship takes this even further. Fully fueled, the combined weight of both stages is around 5,000 tons, but its dry mass is only about 290 tons, just 5.8%. That's incredibly lean for such a massive launch system. So, why do rockets carry so much fuel? They need an enormous amount of propellant to generate enough thrust to lift such a large vehicle through Earth's thick atmosphere and escape the pull of gravity to reach orbit. Of course, having more fuel is good, but raw quantity isn't everything. To truly optimize a rocket's performance, you need specific impulse, or ISP, a measure of how efficiently your engine turns fuel into thrust. Think of it like a car's miles per gallon. The higher the ISP, the farther you can go with the same amount of fuel. That's one of the key reasons SpaceX switched to liquid methane. It can deliver a specific impulse of up to approximately 380 seconds in vacuum, while RP-1 only manages around 300 seconds. That's a big difference. With the same amount of fuel, a methane-powered rocket like Starship could theoretically reach the moon, but if it were running on RP-1, it might only make it about 3/4 of the way there. Many people might wonder, if SpaceX switched to liquid methane over RP-1 because of its higher specific impulse, then why not go all the way and use liquid hydrogen? After all, hydrogen offers the highest specific impulse of any rocket fuel, up to 450 to 465 seconds in vacuum, which is a huge leap in performance. But the answer lies in SpaceX's ultimate goal, Mars. Between liquid hydrogen and liquid methane, methane is clearly the more practical option for missions to the Red Planet. For one, the ingredients to make methane are already available on Mars. Thanks to a chemical process called the Sabatier reaction, methane can be produced directly on Mars by combining CO2 from the Martian atmosphere, which makes up about 95% of it, with hydrogen extracted from subsurface ice. Hydrogen, on the other hand, is much harder to deal with. To use it as fuel, you'd need to extract water, split it via electrolysis, and then cool the hydrogen all the way down to minus 253 degrees Celsius, an extremely low temperature that's hard to maintain for long periods in Mars's harsh and fluctuating environment. Methane, by comparison, only needs to be cooled to negative 161 degrees Celsius. It's far easier to store and handle. It evaporates more slowly, is easier to insulate, and is less prone to leakage than hydrogen. All of this makes methane a much more viable fuel for long-term Mars missions, not just to get there, but to launch back from the Martian surface. And that's why SpaceX chose it. Next, let's talk about combustion temperatures. Cooler-burning fuels are generally easier on rocket engines and can help extend engine lifespan over time. RP-1 burns the hottest, reaching temperatures of around 3,397 degrees Celsius. Liquid hydrogen burns cooler, at approximately 3,097 degrees Celsius. And in case you haven't guessed, methane falls right in between, burning at about 3,277 degrees Celsius. Now, let's shift to another thermal factor, boiling point, the temperature at which each fuel turns from liquid to gas. Since rocket fuels need to stay in liquid form to maintain high density and be easily managed, a higher boiling point makes storage and handling much easier. Fuels with higher boiling points require less insulation to prevent boil-off, and less insulation means lighter tanks, which is always a plus for rockets. Because methane and LOX have similar storage temperatures, they can be housed in adjacent tanks with a common bulkhead, simplifying vehicle design and saving mass. In contrast, hydrogen and LOX have such different temperatures that storing them side by side becomes a major challenge. LOX would boil the hydrogen, and hydrogen could actually freeze the LOX. Speaking of LOX, there's been a huge development. SpaceX has just secured permission to build its own liquid oxygen production plant, right near the South Texas launch site. More specifically, Cameron County has officially approved SpaceX's plan to construct an air separation unit just 300 feet from the local sand dunes. This facility will function much like a small refinery, pulling in atmospheric air and separating it into its core components for rocket operations. The plant will sit on a 1.66-acre plot, about 1.25 times the size of a standard football field, and will include 20 different structures, most notably a 47-meter-tall tower, roughly the height of a 15-story building. The tower will be built around 85 meters inland from the vegetation line at the edge of the dunes. Using this new plant, SpaceX will separate air into liquid oxygen and liquid nitrogen. LOX is used as oxidizer for rocket fuel, while liquid nitrogen is essential for engine testing and general operations. With this facility, SpaceX hopes to eliminate the need to truck in fuel from nearby Brownsville. Currently, the company says it needs over 200 tanker trucks of LOX and LN2 per launch, which costs between $700,000 and $900,000, not to mention the temporary traffic congestion it causes along Highway 4. That's according to a SpaceX engineer who spoke at a county meeting just last week. To put things into perspective, 1.66 acres is relatively small compared to large-scale ASU facilities, like Air Liquide's plant in South Africa, which produces up to 5,000 tons per day of liquid oxygen. A facility on this footprint would likely fall into the medium or small-scale category, more in line with industrial or medical-grade production needs rather than massive national supply. In terms of output, mid-sized air separation units typically produce anywhere from 150 to 1,000 tons of LOX per day, depending on their design and technology. Assuming SpaceX's plant lands somewhere in the middle, say around 500 tons per day, that would equate to roughly 438,000 liters of liquid oxygen produced daily. Even after factoring in electricity usage and other operational costs, the economic and logistical advantages are clear. Instead of relying on hundreds of fuel deliveries from outside sources, SpaceX would be generating its own oxidizer right on site, faster, cheaper, and more sustainably. But as promising as that sounds, there's also a real possibility that SpaceX might abandon plans to build its own ASU at Starbase due to a lack of sufficient on-site electrical power and other practical limitations. Right now, all eyes, hundreds of thousands of them, are locked on Starbase, where SpaceX is pushing harder and faster than ever before to make Flight 10 happen. But this isn't just any launch. This one means everything. After 4 explosive failures in a row, Starship hasn't just disappointed fans, but also key partners like NASA and the Department of Defense. This flight is their chance to turn it all around. If it goes well, the whole program could get back on track. So, what exactly has SpaceX been doing lately to prepare for this critical mission? On July 20th, SpaceX transported a forward flap into the Mega Bay 2. It had already been outfitted with heat shield tiles, clearly intended for Ship 37. The very next day, another forward flap was spotted being brought inside, then lifted by a crane before the doors closed, so no one could see what happened after that. But on July 21st, observers noticed that Ship 37 was still surrounded by a lot of scaffolding. It's possible that by the time you're watching this video, they've already finished installing the flaps and are just waiting for a transport ring to be rolled into MB2. Once that happens, we might finally witness Ship 37 rolling out to Pad A, ready to be lifted onto the giant stool that SpaceX has spent over a month modifying just for it. So how's the progress at OLM Pad A coming along? Let's take a closer look. On the morning of July 18th, SpaceX's massive LR-11,000 crane arrived at Launchpad A. Workers used specialized cables to secure all 4 corners of the giant Starship transport stand. Just 30 minutes later, they lifted it into the air and lowered it neatly into the center of the orbital launch mount, which had been modified weeks earlier with welded I-beams to support this structure. After the lift, crews spent some extra time adjusting the position of the stand to ensure it was perfectly aligned. By the end of the day, the crane was detached, confirming that the structure had been securely seated. Although the stand is now installed, it still needs some final reinforcements and adjustments before it can be fully operational. Most likely, it just needs clamps and hydraulics installed, so it can be easily removed in the future, if needed. This installation marks one of the final major steps in the transformation of the orbital launch pad. What was once just a simple structural ring has now evolved into a reinforced, feature-rich platform, equipped with vacuum Raptor engine mounts, support legs, and steel reinforcements for added durability. The removable module design is intentional, making it easier to carry out the upcoming launch. After all, the stand will need to be taken off again following the static fire test, which is currently expected to take place late next week, around July 31st or August 1st. To support this setup, SpaceX also had to adapt the fueling system, specifically the booster quick disconnect on the OLM, to work with Starship. Over a week earlier, SpaceX also made several key modifications to the BQD system on the orbital launch mount to allow it to interface with the Starship vehicle, since the BQD is normally designed for the booster and not the ship. Its connection layout is quite different from the SQD. To make it work, SpaceX had to rework the high-pressure lines and electrical hookups for Starship. Some of the changes included cutting holes into the back of the BQD hood and installing custom piping that routes propellant lines over the top, connecting them to new support frames mounted on the sides and upper section. It's possible that SpaceX may rotate Starship slightly to one side, allowing them to route the propellant lines through a temporary setup, since the BQD isn't directly compatible with the ship. Additionally, SpaceX may have removed the BQD hood door and kept the quick disconnect plate in the retracted position to make space for the new connections. The new SQD setup hasn't been completed yet, so they'll probably continue working on it once the Starship stool is fully secured in place. Those are the latest updates from Launchpad A. But let's be honest, doing a static fire test, then removing the stool just to launch Flight 10, only to put it back again for Ship 38's static fire, and then removing it again for Flight 11. That's a lot of effort and time. So, while nothing's confirmed, there's a real possibility that SpaceX might conduct static fire tests for both vehicles, Ship 37 and Ship 38, back to back. These are the last two Block 2 Starships before the full transition to the next-gen version. And that's actually quite likely because Ship 38 already had its heat shield system installed as early as June 17th. Most recently, on July 20th, it had its forward flaps installed inside the Star Factory. Some sources suggest that Ship 38 has been built in parallel with Ship 37, with the intention of performing two static fire tests back-to-back. But since Ship 38 is slightly behind in completion, those tests would probably be spaced a few days apart, if that plan moves forward. Alright, those are the latest updates from Starbase. So, what's next for SpaceX as we get closer to Starship Flight 10? According to Elon Musk's comment, launching again in approximately 3 weeks, which he left under a post on July 15th. That means Flight 10 could happen sometime before August 10th. So, yeah, the clock is ticking and SpaceX has a packed schedule ahead. First things first, Ship 37 is expected to go through a 2-stage static fire campaign. The first test will likely involve firing just a single engine, serving as a system demonstration for the newly installed test stand and the updated quick disconnect system. This low-risk test allows engineers to verify fuel flow, ignition capability, and safety systems without putting too much stress on the hardware. Once that's done, the team will need to remove the static fire stand from the orbital launch mount. That'll restore the BQD to its launch-ready configuration, at least. That's the current plan. Then Ship 37 will likely be rolled back to Megabay 2 to receive its test payload, probably a dummy Starlink stack like what we saw on Ship 35. It might include up to 8 satellites, just like before. Even though these are non-functional dummies, they're critical for validating Starship's ability to deploy payloads, because so far, Starship still hasn't successfully deployed a single satellite in orbit. That's huge. After all, one of Starship's main goals is to take over satellite launch missions from Falcon 9. Not to retire Falcon 9 entirely, but to let it focus on other key missions, like launching Crew Dragons, Vast's Haven modules, and commercial payloads for private companies. After the simulated satellite payload is installed, Ship 37 will also be fitted with a Flight Termination System, or FTS. This system is designed to destroy the rocket or spacecraft if it veers off course or encounters a serious malfunction that could pose a danger to nearby areas, especially residential zones or critical infrastructure. It's a crucial step. In previous Starship test flights, issues like fuel leaks or loss of control during re-entry led to the activation of the FTS to prevent an uncontrolled crash. For Ship 37 and every prototype that follows, installing the FTS is mandatory. It's one of the key safety requirements set by the Federal Aviation Administration before granting launch approval for any test flight. Speaking of the FAA, the agency did require SpaceX to investigate the anomaly from Flight 9, just like it has with previous test flights. Normally, these investigations tend to push back SpaceX's launch schedule due to all the red tape involved. But interestingly, ever since Flight 8, SpaceX has still been able to secure launch approval for Flight 10, even while the investigation into the last flight is still ongoing. According to several sources, this shift might be because the FAA is now under increasing pressure from Congress and other parties to speed up the licensing process. Once everything's ready, the pad, the rocket, and all systems, SpaceX just needs to submit the launch license request to the FAA and wait for approval. So if you're excited for what's coming, type 10 in the comments and don't forget to like and subscribe so you won't miss a moment of SpaceX's thrilling journey. Right now, Starship Flight 10 is shaping up to be one of the most important launches in SpaceX's development history. As one of the final two Block 2 Starships, Ship 37 stands as a symbol of relentless effort, and now it must prove that the vehicle is safe. Transitioning to Starship 5-2 brought both excitement and hard lessons. Of the 3 V2 flights this year, 2 ended in mid-air explosions. Flight 9 performed better, but ultimately failed due to a payload bay door issue and loss of control. Leaks have been a recurring root cause behind many of these failures. Even Super Heavy, which has already landed twice, ran into new challenges during Flight 9 as mission complexity ramped up. That's why Flight 10 carries a heavy burden. It needs to pull off a complete flight profile, with both stages working perfectly and meeting all mission goals. For Super Heavy, that means a flawless performance post-stage separation, clean boost back, controlled descent, and landing. It may even require further upgrades to handle the growing demands of future missions. As for the upper stage, it first needs to survive ascent. Vibration control and hardware reliability must improve. Then comes payload deployment, a process that relies on a fine-tuned, reliable door mechanism. Finally, re-entry. The ship will face brutal conditions. It has to stay stable, prevent leaks, and ensure the flaps and heat shield systems hold strong. If Flight 10 succeeds, Flight 11 could attempt the first full catch of the booster using Mechazilla, a huge milestone and a fitting finale for the transitional V2 generation. Success would validate key recovery hardware and give SpaceX the confidence to move on to V3. But even if it fails, the data gained will directly inform upgrades for the next version. To make this happen, SpaceX is moving fast. Booster 17 has completed cryogenic testing, and Ship 38 is believed to be fully stacked in Megabay 2, while COPV issues at McGregor might delay S-38's cryo test. The pause gives more time to fine-tune the systems. These final V2 flights mark a turning point. Flight 10 is about proving readiness. Flight 11 is about pushing boundaries. Now, preparations for Flight 10 are underway. And while things seem quiet now, SpaceX could roll out Ship 37 to Pad A at any moment. The countdown to Flight 10 is picking up speed, and in the end, we'll be proud of what they're striving to achieve. Throughout the history of rocket development, no matter the company, vehicles exploding during testing has always been completely normal. Just take a look at this. You see, SpaceX is no exception, but even though failures like these are expected during early development, they can still come at a heavy cost. When a rocket explodes, it's not just debris. It unleashes a powerful blast and shockwave. Take the Ship 36 incident, for example. It blew up during fueling at the Massey site, and experts estimated the force was equivalent to 500 tons of TNT. The explosion severely damaged nearby infrastructure, with total losses reaching $300 million, including environmental cleanup from debris scattered far from the site. For someone like Elon Musk, money isn't the main problem. It's time and reputation. After the incident, SpaceX was faced with 2 main options. 1, wait for Massey to be fully restored before moving ahead with the static fire test for Ship 37. It's the safer choice, but it also means a serious slowdown. And as you can see, it's already been over a month since the explosion, yet the Massey site is still far from ready. Workers have even been living on site, eating, sleeping, and doing everything they can to speed things up. On July 17th, photographers spotted scaffolding going up around the static test stand, signaling the start of the recovery effort. Now let's talk about the second option, the one SpaceX actually chose. They decided to modify Launchpad A at the orbital launch mount to carry out the static fire test there instead. And there's a good chance Ship 37 might actually do it as early as next week. Just yesterday, SpaceX updated their beach and road closure schedule on their website, listing July 29th as the target date. That timing lines up perfectly with the recent progress SpaceX has made modifying Pad A, something we already covered in our previous episode. But to be honest, this is still pretty risky. It's the first time SpaceX has modified fixed infrastructure like the OLM to mount a new module such as the ring stand and the new SQD. There's always some level of risk when placing a Starship on top of hardware that's just been reconfigured. But the trade-off makes perfect sense because they knew restoring Massey would take at least 3 months. That means Massey wouldn't be ready until sometime around September. And if they waited that long, Flight 10 would end up launching nearly 4 months after Flight 9, basically wasting an entire quarter of the year. That's a big deal, especially when the FAA has already approved up to 25 Starship flights for this year. Now, let's say you were in charge of the Starship program. Would you take the risk to speed things up? Let me know what you do down in the comments. Well, it's important to note that by going with this option, SpaceX is also taking on some serious risks. Imagine if a COPV failure happens, Ship 37 could blow up like a bomb, and Makezilla on Pad A could be reduced to a twisted pile of scrap metal. No chance of repair, only a full rebuild. That alone could set them back at least 6 months, judging by how long it took to build Pad B's launch tower. And if you include the orbital launch mount, the fuel lines, and all the nearby electrical systems, we're talking nearly a year of delays. And remember, rebuilding isn't as simple as starting fresh on a clean site. After a blast like that, the area would be a total war zone, just wreckage and chaos everywhere. So then, why is SpaceX still confident despite the risks? Is it because they've already put solid safety measures in place? Or maybe they've got backup plans we haven't seen yet? Let's take a closer look. On July 6th, SpaceX quietly ran a secret test related to COPVs at their McGregor test site in Texas. A nearby camera caught the moment. A sudden blast, white vapor shooting at least 30 meters into the air, and what looked like a dark object being launched skyward. In tests like these, engineers deliberately push tanks beyond their limits, a process called burst testing. They fill them with nitrogen, helium, or even cryogenic liquids like liquid nitrogen or oxygen to see exactly how much pressure the tank can handle before it gives out. Since then, SpaceX has identified the root cause of the Ship 36 explosion and taken steps to prevent the same thing from happening with Ship 37. For now, the odds of another catastrophic failure during fueling have been reduced to the absolute minimum. Okay, so that covers the risk prevention side of things. But here's the real reason SpaceX is willing to take such a big gamble. From the very beginning, SpaceX has embraced a build, fail, iterate to drive rapid innovation. By running the static fire test right on the launch pad, they're not just testing the engines or the stability of the vehicle. They're checking the entire integrated system, from hardware to infrastructure. This includes all the modified components at Pad A, like the custom stool that now supports Starship on the OLM, and the adjusted BQD arm, redesigned to transfer propellant more efficiently. Testing in this way allows them to spot any hidden issues across the whole setup without waiting for Massey to come back online. And more importantly, it gives SpaceX valuable real-world data they can use to upgrade other launch pads, making them more flexible, more resilient, and less vulnerable to delays like the one caused by the Massey explosion. Next up, what SpaceX is risking here is also about what they'll gain after Flight 10. We all know SpaceX is under pressure from NASA, with over $4 billion in contracts to develop the Starship HLS for the Artemis program, which aims to land astronauts on the moon in 2026. So speeding up tests, including the static fire at Launchpad A, is necessary to stay on schedule. On top of that, Elon Musk's long-term goal is to build a fleet of Starships for Mars colonization. That means they need to test and refine the technology in a short amount of time. Flight 10 will mark the full test of one of only 2 Block 2 Starships. What matters most here is the flight data, how well the PEZ door works, how stable the fuel tank pressure is, and whether the Raptor engines perform reliably. That data will be key to helping them move quickly toward the next-gen Starship later this year. Not to mention, if they've learned from the past 4 explosions, then Ship 37 is their chance to prove it, to show that the vehicle is now stable, holds pressure, flies smoothly to suborbital altitude, and can deploy a dummy Starlink. If that happens, it won't just excite fans. It'll help SpaceX restore confidence from its partners and regain the momentum they've been missing. Overall, SpaceX has come up with a way to reduce the risks during the static test at Launchpad A. And when you combine that with the valuable data they're gathering, it's a risk worth taking. But did you know SpaceX already has a backup plan in place, just in case Launchpad A gets destroyed? Because let's face it, Mechazilla, the OLM, and even the current water deluge system still aren't fully ready to handle a 142-meter Starship launch. So, SpaceX isn't just taking a risk, they've already factored in the possibility of losing the pad. In fact, Launchpad A is expected to be upgraded in the future anyway, with a flame trench added to handle the immense power of the 33 Raptor 3 engines on the Super Heavy Block 3, pushing nearly 10,000 tons of thrust. If a blast does happen, it might actually speed up those upgrades, giving SpaceX the opportunity to prepare the pad for the next-gen vehicle set to debut later this year. And while Pad A undergoes its revamp, Launchpad B will take over and handle the final launch of Block 2, Ship 38. Pad B is now entering its final phase of construction. One of the most significant and recent developments is the arrival of the booster quick disconnect hood, a massive structural piece designed to shield the booster's fueling interfaces. On July 17th, this giant component was delivered to the pad, immediately drawing attention for its sheer size and noticeable design changes. Compared to the current version used at Pad A, this new QD hood is much larger, likely designed to support the upcoming Starship 5-3. These newer vehicles will need more fuel and more complex electrical and data connections, all of which will run through this upgraded interface. Its boxy shape marks a departure from previous designs. Instead of curving to fit into the OLM, this hood has a squared-off modular shape, suggesting it'll be installed on a separate QD structure rather than integrated into the OLM itself. This new approach could allow for easier maintenance and greater flexibility. The hood also features large square cutouts on both ends, providing room for high-flow fuel lines, retractable QD plates, and thermal shielding. One of the cutouts even reveals a cluster of smaller ports, possibly for auxiliary systems related to fueling or control. But this hood is just one part of the full BQD system. Additional components like interface plates, shielding panels, and access doors are still missing. The lack of visible latches or handles suggests those elements are either still being fabricated or will be added later. With daily progress and near constant activity at the site, it's clear that the launch pad is transitioning from the construction phase to the testing phase. So, when will Pad B officially come online? At the current pace, construction could wrap up by the end of this month. But even after that, several early tests will need to be completed, like pressure checks on the plumbing, valve response tests, and system integration checks. That includes the Mechazilla arms and other critical components. If all goes well, the pad could see its first launch later this year, possibly even supporting the debut flight of the next-gen Starship, currently expected to be Flight 12. Back to the point, while Pad A is still operational, signs of wear are starting to show. Discoloration and rust from repeated heat exposure have begun to appear, making it clear that upgrades are inevitable. SpaceX plans to retrofit Pad A using lessons learned from Pad B, replacing the old OLM and steel plate with a flame trench and upgraded systems. This overhaul will likely require Pad A to be temporarily shut down, making Pad B the new workhorse of Starbase. And in the end, the upgrades to both Pad A and Pad B aren't just about sending more powerful rockets into space. They carry the ambitions of an entire company, and maybe one day, the dreams of an entire planet. We're witnessing the rise of infrastructure built not for a single rocket, but for an entire generation. The dawn of large-scale, high-frequency spaceflight depends on 4 launch pads in the future, 2 at Starbase and 2 in Florida. These systems are being built to endure, to adapt, and to evolve. Their impact will reach far beyond this world. Humanity has officially entered the era of space conquest in an extremely active way since the mid-20th century. The first satellites, space telescopes, or space stations were planned and built. This was the time when the first modern spacecraft were launched farther than ever. However, for many decades, the launch cost was still too expensive, and the ship seemed to be used only once. That was also the time when Elon Musk appeared, carrying a great vision that saved everything. He once fell into despair when the initial dream with Falcon 1 kept failing, but with the nature of a resilient person, he did not stop. That was when we saw Falcon 1 take off, and Falcon 9 was born. Reuse? Now, it is no longer a problem. Space missions with low cost, but always the best quality, are no longer imaginary. No one dares to consider it a joke anymore. And now comes the Starship, a bulky sci-fi monster with even more terrifying potential. Excited by the fact that a Raptor engine had been launched for the first time, Musk took to the stage at IAC in Mexico in September 2016 and laid out a seemingly far-fetched vision, a giant rocket system that could take humans to Mars, not just once, but hundreds, thousands of times, until the Red Planet became a second human colony. The system was initially called the Interplanetary Transport System, or ITS, then changed to BFR, Big Falcon Rocket, and finally the name that has gone down in history, Starship. At the time, most of the scientific community and the media were skeptical. This was completely beyond the capabilities of a private company that was still struggling with its Falcon 9 rocket. But Musk didn't need the world's faith. All he needed was time and a desolate patch of land in Boca Chica, Texas. Each prototype was born here, from the Starhopper that flew a few dozen meters, to the Mk-1 that exploded, to the SN-1 and SN-15 that went through many failures. But for SpaceX and Elon Musk in general, every failure was a step forward. And then, SN-15 landed successfully, a historic moment. Now, entering its 8th year of development, Starship is truly changing the game. Starship successfully proved that Mechazilla's chopsticks can catch a hovering ship in the air. 3 super heavy boosters successfully returned to the launch site and were gently cradled by 2 robotic arms, each attempt better than the last. Or the reusability of the B-14's 29 Raptor engines, something that no one believed could be possible. In less than 5 flights, SpaceX has shown us, from basic testing to the first successful separation of the stage, to Starship being able to re-enter the atmosphere and land relatively safely in the Pacific Ocean, all of which are unprecedented in space. Now, with Flight 10 just around the corner, less than a year from Flight 5, it is clear evidence of the rapid development of Starship. Starship is currently halfway through its testing journey with Starship V2. Even though the test results with Starship V2 have not been smooth, each test is always an opportunity for Starship to come back stronger. Musk officially announced the first 3 Starship versions in early 2024. It is clear from the update how deep and ambitious he is for this monster to succeed. But we have to admit one thing. Their speed is making us dizzy. It's too fast, like rocket speed, right? Okay, now let's dive deeper to see the revolution of Starship. If the current Starship is enough to overwhelm the world, then no. Right behind the scenes at Starbase, even more monstrous vehicles are being prepared to roll out. Remember the Starship V1. Do you remember what it looked like? With a total height of 121.3 meters, a full-stack Starship V1 would be taller than the Statue of Liberty, and equivalent to a building with more than 30 stories. It has the potential to carry more than 100 tons of cargo per mission and carry 100 crew members at a time. But for Musk, all that was not enough. Just when the Starship V1 was in its heyday, Musk suddenly switched to the new, even larger Starship V2. In addition to changes in the design of the flaps, the upper stage of the Starship has been extended to more than 52.1 meters. If both floors were stacked together, the Starship would have a total height of 124.4 meters. This ship is capable of carrying up to 150 tons of payload for each cargo transport. But, as I mentioned above, the upper stage of Starship V2 did not work very well. Even the first prototypes of this version, S-33 to S-36, continuously exploded, mostly due to engine problems. Only S-36, which exploded due to COPV problems on the test stand at Massey. In contrast to the anxious mood, 6 nose cones appeared inside the Star Factory. Each failure is a learning experience. These 6 nose cones are proof of this. Starship V3 appeared as a savior, bringing with it a breath of comprehensive improvement. With its powerful Raptor 5.3 engine, advanced flight control system, and optimized heat resistance, Starship V3 will open a new chapter for aerospace. This is not simply an upgrade, but a transformation, a breakthrough leap. V3 shows that failure is not the end, but a springboard to go further. And now, the ship is gradually turning the impossible into reality. Not only that, Starship V3 also makes a strong impression with its massive appearance and futuristic shape. With an overall height of up to 150 meters when combined with the super heavy booster, Starship V3 stands tall like a nearly 40-story building, making it the tallest launch vehicle ever built by humans. Its streamlined appearance, stainless steel body shining in the sunlight, and signature nose cone give it the feeling of stepping out of a science fiction movie. V3 retains the Starship's signature design language, but it's been refined with near-perfect precision. The welds are smooth, the contours are aerodynamically optimized, and the fins on both the nose and tail have been redesigned, not only to look better, but also to improve control during re-entry. No longer a rough prototype, V3 is the embodiment of a grown-up Starship, both iconic and practical. Beneath the rugged stainless steel shell are 6 Raptor V3 vacuum engines and 3 Raptor 3 sea-level engines, allowing it to operate flexibly, both when leaving Earth and approaching other planets. When Starship V3 is officially put into operation, it will lay the foundation for SpaceX's future, returning humans to the moon and building new cities on Mars. Every detail of the Starship V3 design is iconic, a testament to the pinnacle of engineering, and an inspiration to a generation of engineers, scientists, and space dreamers. In an age of ever-changing technology, few vehicles are as technical and epic as the Starship V3. Standing before it, one sees more than steel and engines. One sees the future. But don't rush, because that's not all. SpaceX has another version that was previously envisioned, called Starship 4.0. This version is twice the size of Starship V3 combined. While Starship V1, V2, or V3 all have a diameter of 9 meters, Starship 4.0 will have a diameter of up to 18 meters. To prove this, Musk commented, "Probably 18 million for next-gen system" in late August 2019. Again, in 2024, this respected CEO once again affirmed that Starship will lengthen in the next few years. 10 years from now, there will probably be a much wider diameter Starship 2. So, why does SpaceX want to produce such a giant rocket? It belongs to their ultimate goal, colonizing Mars. This ambitious plan would reduce the number of vehicles needed to deliver cargo to the Mars outpost. SpaceX plans to launch 1,000 Starships during each 26-month delivery period to Mars. However, this ambitious plan would require launching thousands of orbital refueling vessels just to refuel these ships in space. This is a logistical challenge on an unprecedented scale, so a Starship 4.0 would significantly reduce this cycle. Musk's 2016 interplanetary transport system proposal had a nominal diameter of 12 meters, hinting at the idea of scaling up the current Starship from the very beginning. An 18-meter version would reduce the number of Starships sent to Mars from 1,000 to just 250 per trip. Likewise, the number of refueling flights would also be reduced. Not only that, such a Starship will effectively contribute to the construction of infrastructure on Mars. Not only can it transport people, necessary food, and research equipment, it can also provide a perfect living environment for humans on Mars. A huge space after reaching Mars can be reinforced and rearranged to become a base for astronauts to live and work regularly. With an internal space large enough for hundreds of people, the life support system as well as the space structure equipped during the transport mission can be utilized to become a living space. The potential, cost, and time can be seen. In addition, when becoming an official base, the fuel tanks that take up a large space can be cleaned and renovated into a new living and working space. With such outstanding advantages, complexity and challenges will always come. An 18-meter-long Starship will require a completely different design. The development and operational phases are forced to increase. The current Star Factory may not be able to meet the production of this vehicle. The fuel tanks are forced to expand, and the steel rings will be thicker than those currently in use. The production capacity of this vehicle may only be met by the gigafactory that is being planned to be built, but regardless, this is a vehicle worth looking forward to. On the other hand, before Starship moves to the interplanetary transport step, we cannot miss the intercontinental flights. After a series of incredible steps by Starship, the confidence of major aviation and space agencies, especially NASA and the U.S. Department of Defense, is increasingly evident. NASA's official selection of Starship as the lunar lander for Artemis 3 is not only a symbolic milestone, but also a confirmation of the transition from potential partner to strategic pillar of U.S. space. The missions under consideration would result in a surge in Starship launches on 3 fronts: Starbase, Texas, LC-39A at Kennedy Space Center, and SLC-37 at Cape Canaveral Space Station, Florida. Starbase remains the primary prototype development and testing center, but a new gigafactory will be built that will be capable of producing hundreds of Starships per year, even if it is large enough to house and assemble the 60-foot-wide steel rings of Starship 4.0. The new launch site at SLC-37 has recently been cleared for 2 new launch pads. The operation there will be primarily for national security missions under military control. The recent draft environmental impact statement considers 76 launches per year at the site, a number that would be the largest to date. Meanwhile, LC-39A, the legendary launch site that sent humans to the moon, will be primarily optimized for NASA civilian and scientific missions. The site is also being considered for 44 missions per year, including Artemis missions. At Starbase, Texas, 25 missions per year are being planned. The missions here will be fully commanded by SpaceX. New Starship prototypes or new launch facilities like Pad B will be primarily tested here. When SpaceX revealed the Raptor 3 back in August 2024, the rocket community kinda lost it. Everyone was shocked and hyped at the same time. Why? Because this engine looked way too good to be true. The first thing people noticed was the design: super clean, super minimal. All those pipes and external cooling lines you usually see, gone. Everything's been tucked neatly inside. And despite that sleek look, it's still insanely powerful. 280 tons of thrust at sea level, and over 308 tons in vacuum. That's around 22% more powerful than Raptor 2. Some folks didn't even believe it was real at first. They thought SpaceX had just shown off an unfinished engine, like they were only halfway done assembling it, but posted a photo anyway to flex how clean it looked. Even industry experts were skeptical, like Tony Bruno, CEO of ULA. He posted a tweet congratulating SpaceX on the new engine, but also threw in a bit of sarcasm. He wrote, "So, there is no need to exaggerate this by showing a partially assembled engine without controllers, fluid management, or TVC systems, then comparing it to fully assembled engines that do." Just 4 days later, SpaceX's powerful COO, Gwynne Shotwell, responded directly. She wrote, "Works pretty good for a partially assembled engine," alongside a photo of Raptor 3 being test-fired. The engine looked exactly like the one SpaceX had shown earlier, still clean and minimal, now blasting out a powerful blue flame. It was clear, SpaceX wasn't showing off an unfinished engine. They were showing the real deal, and that response definitely shut Tony down. A lot of people probably found the whole thing pretty satisfying, and honestly, a little funny too. It only made SpaceX's efforts even more impressive, proving once again they're leading the charge in modern rocket engine technology. At this point, you might be thinking, all right, Raptor 3 looks done. It's ready to launch Starship into space, right? Well, not quite. Elon Musk recently revealed a tough truth about it. Replying to a post on X, he commented on the Raptor 3's startup system, saying, "Very complex startup sequence. Insane timing precision is needed to avoid blowing up the engine." That statement surprised a lot of people. Many had assumed the upgrades in Raptor 3 also meant a more streamlined startup process. But while the outside looks cleaner and more compact, under the hood, things are still incredibly complex. The startup sequence is still a massive technical hurdle, demanding split-second precision, with absolutely no room for error. So, what exactly makes this engine so hard to start? To understand that, we need to take a closer look at what this engine actually is. The reason SpaceX developed the Raptor in the first place is simple: Mars. To get there, they chose a full-flow stage combustion cycle powered entirely by liquid methane and liquid oxygen. It's an extremely advanced engine architecture, and Raptor is the first one of its kind to ever fly. The first version, Raptor 1, was tested on Starhopper. Since then, with Raptor 3, SpaceX has streamlined the exterior by routing many of the external pipes internally, removing heat shields and protective cladding, boosting turbopump efficiency, and pushing combustion chamber pressure to the edge, right where it can still be kept in balance with the engine's cooling capacity. Unlike simpler engines that use a single turbopump, Raptor runs on two, one for liquid methane, the other for liquid oxygen. Each turbopump is driven by a dedicated pre-burner, one oxygen-rich, one fuel-rich. These pre-burners generate hot gases that spin the turbines, and the engine burns all of that gas in the main chamber. Nothing is wasted. This closed-cycle setup is called a full-flow stage combustion system. It's incredibly efficient, perfect for Mars missions where fuel is precious, but it's also what makes startups so insanely difficult. To ignite the engine, a series of complex steps has to be followed. First comes a phase called engine chill. In this step, SpaceX allows a small amount of liquid methane and liquid oxygen to flow from Starship's propellant tanks into the Raptor 3's fuel lines. These propellants pass through built-in regenerative cooling channels lining the combustion chamber and nozzle. This is critical because if the engine isn't pre-chilled, the cryogenic propellants could flash into gas on contact with hot metal, forming vapor bubbles in the fuel lines that could disrupt the flow or even damage the engine. Once chilled, the next stage begins: spin up. This is when two separate turbopumps, one for methane and one for liquid oxygen, are spun up to high speeds. To ensure a steady flow of propellants, SpaceX uses composite overwrapped pressure vessels, COPVs, filled with compressed helium to pressurize the propellant tanks, pushing liquid methane and oxygen into the fuel lines and turbopumps. Because this process must be continuous and reliable, each booster is equipped with a large number of these COPV tanks. That's why, when the tail section of Booster 13 was recently recovered from the sea, we could clearly see the top of the engine section exposed, with a few big COPVs installed right above it. Once the pumps are spinning, each sends propellant into its respective pre-burner, where a small portion is ignited to produce hot gas. This gas powers the turbines that drive the pumps. But if the pumps don't reach the perfect speed and stay precisely synchronized, the result could be vibrations, instability, or even catastrophic engine failure. When the pumps and turbines are operating smoothly, the next step is to ignite the pre-burners. This is one of the most delicate parts of the entire process. The fuel ratios and flow rates must be exactly right, because if not, the engine could suffer a hard start, a sudden, uncontrolled ignition that can seriously damage internal components. Assuming ignition is successful, the hot gas produced in the pre-burners flows into the main combustion chamber. There, the remaining methane and oxygen are mixed and burned completely to produce thrust. The handoff between pre-burner ignition and full combustion has to happen in a tightly choreographed sequence, timed down to just 10 milliseconds. Even the slightest delay or imbalance can cause serious problems. And once the engines reach full power, the job still isn't over. The avionics system has to constantly monitor dozens of variables, temperature, pressure, and fuel flow among them. And we're not just talking about one engine. Super Heavy is powered by 33 Raptor engines, while the upper stage uses a cluster of 6, 3 sea-level, and 3 vacuum-optimized engines. These two types don't even operate at the same thrust levels or chamber pressures. That means every single engine has to start, run, and shut down in perfect sync during both ascent and landing. The complexity multiplies exponentially with every additional engine. In short, the full-flow stage combustion cycle demands an incredibly high level of coordination between mechanical systems, electronic controllers, and fluid dynamics. That's why Musk keeps stressing the need for insane timing precision. Given all that, what exactly has SpaceX been doing to tackle this problem? Actually, SpaceX already revealed their solution more than 2 weeks ago. On July 9th, the company shared a major update for Super Heavy. The Block 3 version will include a long fuel transfer tube running down the center of the booster. The idea is to use this tube as a sort of secondary fuel tank. It's designed to receive supercooled liquid oxygen and liquid methane from Super Heavy's main tanks, then evenly distribute that fuel to all 33 Raptor 3 engines, preventing interruptions caused by flight maneuvers like belly flips or hot staging. This helps ensure a steady fuel supply even when the rocket is rotating. It also allows for simultaneous engine ignition during launch and landing burns, improving both performance and reliability. Now, during a flip maneuver, the booster experiences acceleration forces of 1 to 2 Gs within just a few seconds. That's enough to shake up the remaining 388 to 775 metric tons of fuel, basically like violently shaking a water bottle. And with LOX having a density of 1,100 kilograms per cubic meter and liquid methane around 430 kilograms per cubic meter, the inertia involved is massive. This kind of sloshing can push the fuel away from intake points, disrupting the flow and causing a pressure drop. And keep in mind, each Raptor 3 engine needs nearly 400 liters of fuel per second during landing. Even a brief pressure drop, from 300 bar to below 200, for instance, could lead to ignition failure. That's where the redesigned tube really makes a difference. It pulls fuel from the main tanks, regulates internal pressure, and channels it through smaller lines directly to each engine, keeping everything stable even under extreme stress. Above all, what we care about most is the Starship upper stage, with 6 Raptor 3 engines that must survive fire from within and fire from without during re-entry. To handle this, each Raptor 3 is wrapped in an actively cooled shell. Tiny channels are built into every outward-facing part of the engine, allowing cryogenic fuel to flow through and keep the metal cool even as temperatures soar. But SpaceX didn't just remove parts, they combined them. Instead of relying on dozens of individual pipes and components, they've begun integrating multiple functions into single assemblies. The number of flanges has been drastically reduced. Now, if repairs are needed, the engine might have to be cut open, but in return, manufacturing gets cheaper. And even though this adds some complexity, the benefits of fewer individual parts often outweigh that cost. Supporting all of this are revolutionary technologies borrowed from outside the rocket industry. Metal 3D printing, which Raptor relies on heavily, allows intricate parts to be printed as a single unit. That's what made the actively cooled shell possible in the first place. Raptor 3 is already the most advanced rocket engine in the world, with unmatched throttle range and performance. But even now, it's still far from what it needs to be to help SpaceX achieve its ultimate goal, becoming a multiplanetary species. Behind the scenes, SpaceX is almost certainly working on Raptor 4, an evolution designed to fix the lingering issues and power humanity's dream of living on the red planet. This upgrade could give Starship the thrust it needs to break past the 10,000-ton mark at liftoff, a critical milestone on our journey to Mars and beyond. But Raptor 4 might be more than just a power boost. It could represent a fundamental rethink of engine architecture, cleaner startup logic, better maintainability, more modularity, and seamless integration with future versions of Starship. So, are you excited for Raptor 4? Drop a number 4 in the comments if you are. And hey, while you're at it, consider hitting that subscribe button. Our goal is 150,000 subs, and every single one counts. Thanks a ton. Before we jump into the main story, there's an important Starship update we just can't ignore. SpaceX has officially announced a major upgrade for the Super Heavy booster, specifically the installation of a brand new fuel transfer tube into the first next-generation prototype of the rocket. What's really striking is the sheer scale of this upgrade. The redesigned transfer tube is nearly the same size as an entire Falcon 9 first stage. It's responsible for channeling cryogenic fuel from Super Heavy's main tank down to all 33 Raptor engines. And with that, it's expected to unlock major performance improvements, like smoother, more reliable flip maneuvers and the ability to ignite all engines simultaneously during liftoff or landing. Elon Musk also added an important detail. It's more of a fuel header tank than a transfer tube. Has to be very buff, as it is subject to extreme loads and a single leak would be game over. This signals that SpaceX is getting closer than ever to making Starship a stable, high-performance, and rapid launch vehicle. Now, let's get back to the main point. Co-PVs, or composite overwrapped pressure vessels, have quickly become the most talked about component on Starship right now. And for good reason. People are wondering, how could a part that's supposed to be ultra durable and costs just a few $dozen end up causing a catastrophic failure that dealt hundreds of millions in damage to SpaceX's infrastructure and timeline? The engineers were just as concerned. They immediately launched a deep dive investigation to find the root cause of the explosion and, more importantly, how to prevent it from ever happening again. Because without a solution, no one can guarantee that a similar accident won't strike in the future. And given that the Ship 36 incident alone has already set them back by at least 2 months, the pressure to solve this is higher than ever. On July 6th, something unusual happened at SpaceX's McGregor test site in Texas, the same place where they are currently building Raptor 3 engines for the next-gen Starship. A nearby camera caught the moment, a sudden blast, white vapor shooting up at least 30 meters, and what looked like a dark object being thrown into the air. It didn't take long for experts to start speculating. This was likely a dedicated COPV test. And not just any test, it may have been designed to simulate exactly what happened during the Ship 36 incident. In these kinds of tests, engineers often push tanks past their limits, a process called burst testing, by pumping them full of nitrogen, helium, or even cryogenic liquids like liquid nitrogen or oxygen. The goal? See how much pressure they can take before something gives. But that might not be the whole story. This could have also been an environmental test, where they mimic real Starship conditions, like super low temperatures or repeated pressure cycles. That helps reveal any weak spots in the tank, uneven fiber wraps, a flawed liner, or a bad weld. And if there's a defect, the stress can crack it wide open, sending the tank flying and releasing a huge burst of vapor as the cryogenic liquid instantly boils off. By recreating this kind of failure in a controlled setting, SpaceX gets a much clearer picture of what went wrong and how to fix it. These tests are a critical part of making sure Starship flies safer, stronger, and better in the missions to come. So, the big question now is, what exactly did they learn from that test? And more importantly, how does it help improve Starship Flight 10 and every future launch after that? Well, the co-PVs SpaceX currently uses for Falcon 9, Falcon Heavy, and Starship are Type 3 composite overwrapped pressure vessels. These tanks feature a metal liner, usually made of aluminum, wrapped with high-strength composite fibers like carbon fiber or fiberglass. This design allows them to handle extremely high pressures while keeping weight down, which is essential for spaceflight. In terms of performance, these tanks can typically withstand maximum expected operating pressures ranging from 200 to 700 bar, or about 2,900 to over 10,000 psi, depending on the specific design, size, and use case. Now, in burst testing, Type 3 COPVs are pushed far beyond normal limits. They're often tested to 1.5 to 2 times their rated operating pressure. That's anywhere from 300 to 1,400 bar until they rupture. So in this recent test, SpaceX engineers likely gradually increased internal pressure, carefully controlling the flow of gas or cryogenic fluid into the tank until it failed. That allows them to measure the true failure threshold, and from there, adjust the actual flight pressures to stay well below that limit. The end goal? Keep enough usable volume in the tank for flight needs, while adding a larger safety margin, reducing the risk of failure during ascent. Tests like this play a central role in refining the overall Starship system. Both Elon Musk and SpaceX have confirmed that this recent COPV failure was unlike anything they've seen before. Musk noted that a nitrogen COPV failed at a pressure lower than its rated test pressure, a serious issue, especially given the critical role these pressure vessels play in the vehicle's operation. To understand why this matters so much, it's worth looking at what COPVs actually do. They handle tasks like nitrogen purging, flushing systems clean, and pressurizing the turbopumps to spin up the Raptor engines. These tanks, typically filled with high-pressure helium or nitrogen, are essential to engine operation. If a COPV can't maintain pressure, it can trigger a chain reaction that threatens the entire propulsion system. And with each Raptor 2 engine producing up to 230 tons of thrust, and even more expected from the upgraded Raptor 3, the reliability of these pressure vessels is now a top priority for SpaceX. After the Ship 36 explosion, believed to have been caused by a ruptured nitrogen COPV, SpaceX is focusing on eliminating any failure points that could jeopardize upcoming tests or future flights. The immediate goal is to ensure that every COPV can survive burst pressures of 1.5 to 2 times their rated operating pressure, roughly 600 to 1,200 bar, while also withstanding the extreme conditions of spaceflight. That includes cryogenic temperatures below -195 degrees Celsius when exposed to liquid nitrogen, as well as intense vibration and stress during launch. Beyond the engineering, SpaceX is also working closely with reliable COPV suppliers, making sure these tanks are better integrated into the rocket structure, with zero tolerance for defects, both before and after flight. Put simply, this simulated failure test at McGregor is a very good sign. It shows that SpaceX is actively working to validate and improve this critical system before moving on to high-risk operations. Right now, Ship 37 is inside Megabay 2, awaiting its static fire campaign. That gives engineers a perfect window to implement COPV upgrades and make any other necessary adjustments before the next phase of testing begins. Now that the COPV issue is being addressed, the next question is, how is Ship 37 being prepared for its upcoming flight? Yes, we all know that SpaceX has been modifying the orbital launch mount, reinforcing it with steel frames and support beams to install the Starship stand directly onto the test pad. More specifically, they've been welding the support structure straight onto the OLM, using several I-beams mounted to the top platform. The goal? To place Starship directly on top and perform static fire tests, not just for Ship 37, but possibly for Ship 38 as well. But there's a catch. They'll need a separate ship quick disconnect system to fuel the vehicle, and recently, a new ship QD arm has been spotted inside Megabay 2. It's still unclear whether this one is meant for Pad A, which is being prepped for static testing, or for Pad B, which hasn't had any ship QD system installed yet. That said, using this arm for static fire testing on Pad A seems more likely, especially if Starship is placed directly on the OLM without being lifted by the launch tower. Everything seems to be lining up for an upcoming static fire test of Ship 37, assuming the COPV upgrades are completed in time. Unlike previous tests that mostly focused on engines and tanks, this one will zero in on COPV data, offering a rare real-world environment to validate the redesigned pressure vessels. A static fire test is currently expected to take place in mid-August. Following standard procedure, SpaceX will likely bring Ship 37 back to Megabay 2 afterward for inspections, analysis, and any final installations or upgrades. Once that's done, the OLM will be restored to its original configuration, with all the I-beams and support frames removed in preparation for Starship Flight 10. However, there's a major consideration this time. Unlike the earlier incident at Massey, this upcoming test will happen on Pad A, the main launch site. That means any mishap here could potentially damage critical infrastructure like the launch pad, the tower, or even nearby propellant systems. And that would lead to far greater delays than before. That's why the success of this test is absolutely crucial. If all goes smoothly, we could still see a Starship launch before the end of the month. Based on the current status of both the booster and the ship, that timeline still looks feasible. And this upcoming flight, the 10th, is shaping up to be a milestone moment. In terms of mission objectives, Flight 10 will likely pursue many of the same goals as previous flights. Achieving a clean ascent, reaching orbital velocity, deploying a test payload, verifying engine performance in space, and eventually executing ocean splashdowns for both the booster and the ship. The goal is to iron out lingering issues from earlier flights and build a stable foundation for future missions. This flight could also help SpaceX accelerate toward major year-end targets, with one of the top priorities being to successfully land both stages. That would mark the true beginning of full reusability, a game-changing step toward the company's long-term vision, including proposals for launching up to 25 flights per year from Starbase alone. And to support that kind of rapid launch cadence, SpaceX is now building an Air Separation Unit, or ASU, right at Starbase. It's a huge step toward producing their own liquid oxygen, or LOX, the essential oxidizer that powers the Starship's Raptor engines. In the near future, SpaceX won't need dozens of LOX tankers driving in every week. The new ASU will extract oxygen, nitrogen, and argon directly from the air using cryogenic distillation, reducing reliance on outside suppliers, cutting costs, and simplifying logistics. It's all part of a bigger push to make Starbase fully self-sufficient, especially as launch frequency ramps up. Starship launches demand a massive supply of liquid oxygen, and by producing it on site, SpaceX gains better control, more reliability, and fewer bottlenecks along Highway 4, the only access road to the site. The facility will cover 4.85 acres just north of Highway 4 and include 20 separate structures, all packed into a relatively tight industrial footprint. It's yet another sign that Starbase isn't just a launch site. It's becoming a fully integrated production hub for SpaceX's most ambitious missions. The project is expected to be completed in the next 8 to 12 months. So, what do you think? Are you excited about this major upgrade? If you are, make sure to hit that subscribe button. We're on the road to 150,000